I'm going to use the chalkboard. I'm going to try and write really big, but if you're at the back and you can't see, feel free to drift forward. We're all friends. I want to talk about, ooh, yeah, great. Thanks, Dave. Did someone want to call security about this guy stealing a computer?
All right, very well.
I'll just push the board up. Be forward and holler if you can't see. I want to spend a lot of this talk just talking about a really basic object, and just a fundamental example that I've been thinking about since I was in grad school, and I'm still thinking about now, as a way to introduce, both some very, very classical questions, and also some seemingly kind of in the same vein current open questions, but ones that I think now is the right time to attack. And so what's this basic object? We're going to talk about circle bundles over surfaces. So informally, right, you take some surface and you attach a circle to every point of it, okay, in some kind of a continuous way. Okay. So for example, you could just take a product. So sigma g, that's going to be my genus G surface. Here's a sigma 2. You could just, build a topological space. That's a product. That's a circle attached to every point. Okay. So that's maybe example 1. But here's another thing you could do to attach a circle to every point on a surface. You could, say, put a Riemannian metric on your surface. Okay, so one way to do that is just embed it in space like I did here in R3. That's a good way to do it. If you are a hyperbolic geometer, maybe you want a metric of constant negative curvature, do whatever you want. And then look at the unit tangent bundle, or the set of unit tangent vectors at each point. So this is denoted UT sigma g. So if you really are just a surface embedded in space, then, at each point you have a literal tangent plane, and at that point I'm going to take the unit circle in that plane. Okay. That's a great way to attach a circle to every point of your surface. And, precisely the definition of what is a circle bundle over a surface, maybe I'll just, right? Yeah. You have some three-dimensional space. I'll call it E, with a map to your surface. Okay. So that the fiber of this map, the preimage of any point, is a circle. Okay. And they have to be attached to the surface continuously. Just says that locally. So if I look at the preimage of some open disk in your surface, okay, this looks like your disk across the circle, and the P map is just project onto the first coordinate, or the first to the disk part. Okay. So that's a precise reminder of what it means to be a fiber bundle. Okay, but you should just think of that you've attached a circle in a canonical way. Okay, so here's my question number 0 to warm us up this morning. I gave you 2 examples. Question, are my examples 1 and 2 the same object? something you can just ask. That's the, the best question in mathematics is, when are two things the same thing? Okay. Well, let's answer this as a way of getting started off. Let's note a feature of example 1. Okay, is that, well, as you can think of it two ways. There's a circle attached to every point of a surface, but you could also think of it as a circle with a surface attached at every point, right? It's got a product structure, okay? Or another way to say this, if it's really surface cross the circle, I'm bad at drawing a product, but let's pretend my circle is actually a line for the sake of picture. It's one-dimensional. It's the same kind of thing. There's an embedded surface in this, right? So if my projection map is just look at the surface part, it has what's called a section, namely a map from the surface into this object, into the bundle, so that if I compose S with P, I get the identity map. Okay. So this has a section, which is a map section from your surface to the space. Here I was calling it E. Okay. So that S composed with P is the identity on your surface. Just embed your surface as surface cross a point. Okay, so we can ask if 2 has this feature, and if it doesn't, then we've distinguished them in a nice way. Okay, so maybe our next question is how to tell if a bundle has a section. So secretly here, I'm sort of taking you through the history of fiber bundles. And we're here in like the early 1900s at the moment, but we'll get to the year 2000 in not that much more time. It's a rapid history course. Okay, so this might be something that some of you know the answer to or know approaches for, know fancy words like characteristic classes. But I want to illustrate an approach to this problem that's not usually the way you see it. And one that I find like kind of very enlightening in this case. Okay. So let's just try and build, naively kind of build a section for this, for number 2 or for any bundle and just see where we get stuck. Okay, I'll get some colors. So more generally, given a circle bundle over some surface, how can we tell if it has a section? Okay, so how can we tell if it looks like this example 1 where there's secretly sort of a surface sitting inside of it? Well, my answer is we'll just try and build it. Okay, so here's my object, always the same picture, and let's cut it up and then glue it back together. So if I have a surface like this, I can cut along some curves. I'm going to cut along these ones. Okay. And maybe I'll use other colors for these ones. Okay, so I'm going to cut along these curves in the surface, and I'm going to cut all the circles that are sitting over them. And if you cut along all these curves in your surface, the surface, you can then flatten it out. It has no fundamental group left. You can flatten it out, and it'll look like an octagon. So, trust me, I've done it before. I'm bad at drawing octagons, though. 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. And to glue it back together, you want to attach this side to that side, this side to that side, and similarly these ones in pairs. Okay, so that's just the surface part, but remember I have a circle sitting over every point of this. Okay, but as I unroll it, I can really flatten it out to this octagon cross circle. Okay, so for instance, the circle over this point at the intersection of all those curves will appear 8 times, once at every vertex. Okay, so these are all the same, and if I glue this back together in the right way, I'll recover my object. Okay, so you can think of just as, you can think of this as disk cross circle with some instructions to glue it back together. That's how you get your circle bundle over your surface. Okay. Clear on this picture? Great. Okay. So I know there's all my things. If you just look at sort of what's happening around the boundary here, I have an octagon cross a circle. So there's like a whole tube going around. Okay? That's something I maybe could realistically draw. Here's a cylinder, but really this extends, it circles all the way through the middle. Okay, let's try and build a section of this bundle. So what that means at every point in the fiber, I want to pick out a point that will be S of that point in my surface. Okay, and I want to do that in a way so I actually get a continuous map from the surface into this space. Okay. So let's just see what happens. If this is my point x, I'm supposed to choose some point on this circle that will be S of x. Okay? So suppose I do this. I'm here with some point, some candidate for my section. So let's build S. Attempt. Okay. Well, so except this, I can't just choose this willy-nilly. This circle I drew was the same as this one. Remember, they came from cutting this apart. Okay, so however I unrolled this thing, this point will appear on each of these. Okay, in some place it depends on how I unrolled it and flattened it out. Okay, so picking a point here gives me, something in each one of these. Okay, that I'll glue up to give the same point there when you identify all the sides. Okay. Okay, so I've now picked a point that's supposed to be the section over a particular point in your surface. I'm doing this skeleton by skeleton. I took that 0 cell, if you like, in this decomposition, and I built a section over the 0 cell. Let's do one of these lines, a 1 cell, if you like. So all I have to do is on this cylinder sitting above this line, pick a point on each circle. Okay? So I can do that just by playing, connect the dots, if you like. Okay. You could have wound around a couple times. I don't really care what you do. Make a choice, and we'll see if this works out. Okay. So remember, this side is the same as this one. So there's some identification map that takes this to here. So if I choose a path here, that corresponds to a path here also. Okay, so maybe this now winds around. Here I've got a cylinder. It winds around and whoop, comes over here. Okay. Oh, so I'm allowed some choice, but something else will be determined. Okay. So I can continue. I have another side. I can try and play connect the dots again. Maybe I can connect these nicely. But then this side's identified with that one, so this will tell me what happens over here. And I have no control, right? It comes from this gluing map. This was some object that cut apart. It gets glued back together. Maybe here it wound around a bunch of times. Okay. So we do this, and you have some choices, but in the end, you get your section over the entire boundary of this. Well, it'll look like something. I don't know. Okay. On the boundary of the octagon, I can think of my section S restricted to the boundary is a map from this boundary, which is topologically a circle. I'll draw it this way, so we remember what it was. Okay. I can then, well, it goes into the boundary across a circle, but I can project to the fiber direction, and I can just sort of see what it's doing on each of these. Okay. So So I'm going to see what I did here. I just tried by hand to build a section. And what I got is over here I get some kind of curve going around the boundary, which is a circle across a circle. And I'm going to just see what it looks like on the second factor. Okay. And we're going to count how many times this winds around. Okay. If it doesn't wind around at all, if the degree of this map is 0, if it really just looked like effectively a straight line, then I can fill that in with a disk. Okay? And that'll give me a section over the whole thing. But if it winds around a lot, there's no way to extend that to a disk in the middle. Okay? So in other words, the degree of this map okay, if non-zero, means that it can't be extended over the disk or over the interior of the octagon. So I found exactly sort of the thing that says if you try and build a section around the edge, can you extend it over the middle? I found the obstruction to doing that. It's the degree of this windy around map. Okay. Okay. Do people see what this map is? It can be confusing the first time you see it. I'm following this around and I'm tracking where the blue curve goes on these circles. So it looks like in my picture I'm kind of heading up first, and then maybe down a bit, and then like around once more. And then I wind a lot of times, and then I stay there for a second, and maybe go backwards. And so you're tracking kind of the winding number of this. Okay. Okay. Okay, so what I just explained by picture is a classical invariant called the Euler class or Euler number of your circle bundle. Okay. So this, namely the degree of what we just built, it's some integer, and it's called the Euler number of, what did I call my bundle? Okay. So the way I built it depended on lots of choices. I was like, oh, attempt to build a section, just pick a point, you know, play connect the dots however you want. The lemma to prove is that this number is independent of choices. Okay. Questions? If you've sort of seen this, some people probably seen characteristic classes or something like this from the perspective of vector bundles. This is the same Euler class or Euler number, but presented in a slightly different way. So you might want to think about how these match up. Okay. Okay. So hopefully this picture is something you can kind of digest and fiddle around with a little bit more. But let me answer this question by saying that if you do this, so here's the answer to my question. Okay. If you do this little exercise with the unit tangent bundle, you find that it has Euler number equal to the Euler characteristic of your surface, okay, which depends on the genus. It's minus 2g plus 2. And I'll draw you a picture in a second that will give you a hint at how to do this. But right now I want you to take my word at it for it. Why else would they have used the word Euler to call this number? It's the Euler characteristic of your surface. Okay? So it doesn't have a section. Okay. And so it's not the same thing as example 1. Okay, so at this point I've sort of taken you out, we're at like, I don't know, maybe like 1935 or something, where Stiefel and Whitney are talking about characteristic classes or obstructions to bundles having sections. Okay, but I'm only interested in circle bundles over surfaces now. Okay. I want to take one more step, but first, questions, more pictures, clarification. Okay. Yeah. Yeah. So what did I do here? I want to cut along enough surface so that I kill all the fundamental group, right? So I actually can flatten my surface into a disk. So there's lots of choices for what you can do, but one thing you do is you cut along a curve. This simplifies your surface somehow. So if I cut along this first curve, I'll get something that looks like, what have I got? So that won't be this. I'll just have some kind of like open cylinder like this. You know, it looked like this. Whoop. So I've made it simpler. It now is like a genus 1 surface with 2 holes. And I want to cut that open again. So maybe I'll cut along another curve to make that simpler. Okay? And every time I still see some fundamental group left, I should cut along further. Okay? So you can do that just one at a time by hand. I've had enough practice that I know these ones work quite nicely, and this is how it glues back together. Okay. Other questions? Yeah?
What if G is 1?
What if G is 1? Oh, yeah, G is 1, then you do have a section. It's great. There's no, yeah. Okay. Here, secretly, G was 2, but it's the same problem if it's anything better than 2. Let's say unless G equals 1, in which case you're good. Great. Thanks. Yeah? Yeah, so let's see what this looks like. Let me draw a picture. So what I have is I have the boundary of my disk, okay? And I have over every point on the boundary circle, but I'm going to draw it so it looks like a line, and we'll just say that this top part is the same as that bottom part. You come back around. Okay, so it's like I've got a kind of a cylinder going here. And I want to know, I've got some curve sitting in here, and I want to know when is that the boundary of a disk? Okay. Well, if it's the boundary of a disk, I can fill it in. You could think of it being contractible or being able to smush it down to a point. That's what degree 0 looks like. Okay, I'll draw you a picture to see if it's non-zero, something like this happens. Okay. So you are going around this direction multiple times somehow. Okay. And that kind of thing, this kind of helix or something, will not be the boundary of the disk. Okay. So precisely, you need to say something from the world of differential topology. But this is the picture of why non-zero degree, sort of making progress upwards, looks different from the boundary of a disk. Is that good enough for 2 seconds in a talk? We should talk about this. We should talk about this after. Okay. So this is something like degree 1. Okay. And it's not, it's different from degree 0, okay, which is something like this. Okay, other questions? This is great. You should direct this talk to learn what you want from it. Okay. No, okay. Last chance? Great, so let's go on to kind of the next best thing. Okay. So what I want to sort of move on to now is to tell you this unit tangent bundle example. It does have kind of the next best approximation. Okay, so I have to tell you next best approximation to a section. I have to tell you what I mean by that. Okay. So one thing when you build one of these objects, or let me do the product one. Okay, here's my product of surface and circle. Okay, the fact that I have a circle attached to every point, this works regardless of whether you're a product or not, gives me kind of a preferred direction at every point in my space. Namely, I'm at some point. Okay, I can proceed clockwise along the circle. Okay, and the unit tangent bundle, okay, here's a space. It's three-dimensional. I can at any point, so that means I have a point on my surface plus a tangent vector. I have a good direction to go, namely clockwise around the circle. Okay, that's a path, or I guess I drew anti-clockwise. Pick one, anti-clockwise around the circle. That gives me, you know, a direction to move in the space. Okay. In the product one, I also kind of have a transverse direction. Okay, so there's a going clockwise around the circle. Or if this point in the surface cross circle is, I don't know, x in the surface, s, let's call p in the circle, I can keep p constant and move horizontally through my surface. Okay? Gives a transverse surface or piece of surface to this direction. Okay. So you can ask, I have something that maybe doesn't have a section, but I can ask, is there a good notion, not just of how to move in the circle direction, but how to move in the non-circle direction? That is what I want to mean by the next best approximation. Okay. Okay. So instead of putting surfaces in there, I just want to kind of locally put them in there. Okay. Okay. So let's edit this to come up with a more general concept. Here's a definition. And let me tell you, it's exactly this. It's saying, can you at every point pick out a direction that's not the circle direction, okay, in a continuous way? Okay. This is called a foliation of your circle bundle E is continuous, and technically the word here is integrable choice of horizontal, so not the circle direction, but something transverse to it, plane at each point. Okay. So in the product, when I have this, just say what's tangent to the surface part. Okay. What's tangent to the p equals constant? What's tangent to the p equals constant? In some more complicated space, I might not have that being a whole surface, but I'll have some kind of crazy pieces of surfaces at each point. Okay? So I want to say, can you pick out a horizontal direction so that you can always just keep walking along the horizontal? Okay, so this might be confusing. You're like, how can you do this without just putting a surface in there? Let me show you how to do this on the unit tangent bundle, and maybe that will illustrate what this looks like. Okay. So let's illustrate this, and this will give you another way of thinking about the unit tangent bundle. Okay, so here I'm going to assume G is at least 2. And for my picture, I'm going to assume it's equal to 2. Okay. So far we've been doing a lot of topology, looking at spaces built out of other spaces and curves that wind around them. I'm going to move on to a flavor of geometry, and in order to draw a good picture. Okay. So on a surface of genus at least 2, you can always put a metric of constant negative curvature. This will not look like the metric when it's embedded in a plane. You can't embed it in R3. You can't embed such a thing. But you can put one on there. So let's put a metric on your surface of constant negative curvature. Okay. This negative curvature may be -1. Okay. The reason I want to do this is now the universal cover looks like a simply connected space of curvature -1, and that's the hyperbolic plane. Okay. So I can draw, maybe I'll use this other board, draw a nice picture of its universal cover. Okay. Okay. So I'm drawing the Poincaré disk model of the hyperbolic plane. If you haven't seen this, it's like those Escher drawings where things shrink around the boundary. But now if I do my picture from before, I saved it. And I cut along these curves. If I cut along geodesic representatives for them, my octagon will sit inside here looking something like, well, geodesics in this space are curves that meet the boundary at right angles. So my octagon will look something like this. And this will be a fundamental domain for your surface. Okay, so this whole space will be tiled by copies of these little octagons, okay, that look more and more distorted as you get to the edge. But that's just the model we're using to draw the picture. Okay. Elements of the fundamental group are deck transformations. Okay. So they move this tiling. They're symmetries of this giant tiling that I'll have. Okay. So there's one that takes this side to that side, just like in my gluing. Okay. Okay. And an example of how this is glued back together. Okay. And these act by isometries of this space. Okay. So my deck transformations are now isometries, and this is nice. Okay? What I've also done is I've built a new circle that's the boundary of this space. So we use a particular model for hyperbolic space. It's got a circle at the boundary, and isometries extend to maps of the boundary. Okay. Can I get a sense how many people have seen some hyperbolic geometry before? Good. I would say not everyone, but most people. That's great. Ask your friends.
The hyperbolic plane on their name tag.
Ah, great. Cool. All right, so if you need a refresher after, come to me. Great. Okay. Okay, so what do I got? I've got now deck transformations acting by isometries, and these extend to maps of the boundary. So I've actually built kind of a big universal circle here, which is doing something special. All right, let me tell you how to think about the unit tangent bundle. So of course, at every point, I have a circle and tangent vector. Okay. Okay, but the problem is I have like a different circle at every point. Okay, but there's a way to map this all onto the same circle. We can define an endpoint map, take the geodesic that has this tangent to it, follow it in whatever direction it goes. Okay. You can define endpoint map from the unit tangent bundle of the universal cover to the circle, the boundary of the hyperbolic space, if you like. Okay. Okay. It's the endpoint, follow the geodesic, see where it hits the circle. Okay, so if this vector is V in my unit tangent bundle, here is, let's call it endpoint map E. Here is E of V. Okay. So now, pre-images of points under this endpoint map. What's the pre-image of a point? Oh, it's all the tangent vectors that point in this direction. Okay. Okay. That picks out over every point in my surface a tangent vector. Okay. That's almost like a section. Okay. Gives one vector what do I want to say here? I guess looking at the pre-image is locally two-dimensional object inside your tangent bundle. Okay. Okay. So if I just look at a little chunk and I want to know what the pre-image of this endpoint is within this chunk, well, it's all the vectors pointing at this. That's one per point in my surface. Okay. So that looks like a nice little chunk of surface sitting inside my unit tangent bundle. We have to make sure it glues up all right, right? Okay, yeah, so let's check that. Let's check about this gluing with this map A. Let me make it easy on us and take, I don't know, maybe the tangent vector to this side. Okay, so here is E of, let's call this V1. Okay, and A is supposed to glue this side to that side, and it's an isometry, so it sends geodesics to geodesics. Okay, so it's going to send this one to this one. Okay, it goes like this, whoop. And it will take tangent vectors to geodesics to tangent vectors to geodesics. So here's A of V1. It's the tangent vector to this side. Okay, if I follow it to its endpoint, I'll get, here's E of A of V1. Okay. Oh, but wait, A sent this geodesic to that geodesic. So this is actually the same thing as A of E of V1. So it's equivariant with respect to vector transformations. If you like, everything glues up nicely. Okay. I didn't have to choose the one that was tangent to this side. You could have drawn any other geodesic. I just already had this one drawn down, so it's nice. Okay, great. So now in my two examples, both of these, I have sort of notions of local horizontals. Okay. And I'm going to switch these. Well, let's see. I should probably leave that one. Let's go over here. Okay, so here's a question. Does every circle bundle over your surface have a foliation? Okay, if not, which ones do? So in my two examples, there was in both there was kind of a natural way to pick out a horizontal direction continuously, so you can keep walking forever. We go over the edge of the fundamental domain, it glues up. Okay. And the answer, okay, is the answer to a famous question, which now takes us to about 1970. It's a theorem of Wood building on work of Milnor, called the Milnor-Wood inequality. Okay. What Wood observed is that you have a foliation if and only if that number that we defined before, the degree, the Euler number, the thing that measures how far away you are from having a section, the Euler number in absolute value is less than or equal to the absolute value of the Euler characteristic of the surface. So you can build circle bundles with any possible Euler number, but only a small number of them, only a finite amount, have this nice behavior. And somehow this unit tangent bundle is the most complicated one. All right, so I don't think I'll give you the proof, but I'm going to tell you how they think about this to prove this. Okay. Because that'll take me into things that I think about right now and that maybe you should think about, and questions we still don't know the answer to. Maybe now is a good time to advertise. Let me spoil a punchline, okay, so that you're motivated to pay a little attention. There's a question with an answer. Here's a question with no answer, okay, which for the moment I'll just state vaguely. Okay, we know when circle bundles have this foliation. How many, or describe all, different foliations can a given circle bundle have? Okay. So since the 1970s, we've sort of known exactly what spaces, you know, can be sort of striped in a good, nice horizontal direction. As of this day, we don't know what these actually look like. Right? That's a really basic question. I'm just talking about a three-dimensional object. I built it out of a two-dimensional and a one-dimensional object. Okay, I'm asking, what does it look like? And the answer is we don't have a good answer. So I will come back to this in a second and make this more precise, the kind of thing you would actually try and solve and write a paper on. But I want to indicate where we are in our knowledge. Okay. So let me tell you how to build examples. Maybe that's a good way to start. Okay, let me give you a recipe. For constructing an example. In fact, this recipe will work to construct every possible example. Okay, so here's my recipe. It has two ingredients. Step one is you look at the fundamental group of your surface, and you take a homomorphism let's say phi, from the fundamental group to the group of homeomorphisms of the circle. Let's say you preserve orientation if I want my object to be orientable at the end. Okay. Okay, so for example, I could take the trivial homomorphism where everything goes to the identity. Okay. I could take, I could put this, and I could do that bound reaction of the fundamental group. Okay. On the edge of hyperbolic space, okay, coming from some hyperbolic structure. Okay, so e.g. Trivial, or I could put this into PSL2R like you're doing isometries of hyperbolic space, and I could think of this as acting on the boundary of hyperbolic space, actually by Mobius transformations. Oh, sure. I lost. Okay. Okay. So take it, but it can be whatever you want. Okay. There's two examples that look very different. Anything you want, though, is possible. Okay. And two, I'm going to use this to just build a space. Okay, so take the universal cover of your surface, take the product with a circle. So it's like this picture I'm recreating. Okay, and I'm going to form a quotient space by identifying a point in the universal cover and a point in the circle with the image of this point under a deck transformation, and the image of P under the action of this guy on the circle coming from my homomorphism. Okay. If you're doing PSL2R, this is exactly what we were doing here, gluing things back up together. Okay. This is a circle bundle over your surface. Just projecting to the first factor gives me a surface. That's the projection map. Okay. It has a circle over it attached at every point. And it has a good horizontal direction that comes from this direction upstairs. Okay. So in some sense, it's exactly what we did here, but I just artificially built it out of any homomorphism. If you take the trivial one, you will get the product that we had before. If you take this one, you'll get that, but you can do anything in between. And the fact is that any foliated bundle is attainable by this recipe. Okay. Well, here's the fact, is that this builds everything. Okay, so what have we done? I've introduced sort of a basic object in topology. I told you sort of a special example that you can think about using a hyperbolic structure in a boundary action, doing some geometry. Here I've kind of translated it into a problem in about representations of groups, if you like, or about homomorphisms. So the upshot, okay, is that this thing I'm now interested in, foliated bundles, something we've been interested in since, Milner and Wood in the 60s and 70s. Foliated circle bundles over a surface. Okay. These are in bijective correspondence with the set of homomorphisms of your fundamental group to the group of homeomorphisms of the circle. So answering that open question is really something about about understanding this Hom space or this representation space. And remarkably, this is just a thing that we don't understand very well. Okay. Maybe I should tell you the other way. What did we do here? I gave you a recipe that takes something here and builds something there. Okay. So this was the recipe. Okay. To go backwards, how do I do this? Let's go to my picture. Okay. I have a horizontal plane at each point. If I want to sort of figure out how to get my fundamental groups, here's a curve A in the fundamental group. I want to say what is phi of A, a homeomorphism of the circle. Well, you can take the fiber over the base point. That's a circle. Here's my base point. Okay. And I want to define a homeomorphism of this using my curve A. Okay. Well, pick any point. Okay. It has a horizontal direction, like this one. Maybe I should pick the one already in my picture. Okay. So I can follow around my curve. I can lift my curve, keeping it horizontal, to something up in here. Okay. This is not just a surface sitting in there. It might wrap around in some strange way. But if I keep following this, I'll end up somewhere back over the base point, but maybe at another point. Okay. Okay. So this is called taking the horizontal lift, and I'll define that to be phi A of x. Okay. And you check that this is a well-defined homomorphism from your fundamental group. It behaves well with composition to the homeomorphisms of this fiber. Okay. Okay. So this is called horizontal lift, or sometimes called holonomy. Okay. end with a precise question and exactly what I've been thinking about and what I've been working on. Okay. That brings us to 2018, say. So here's the question. It's a precise version of how many different foliations can a circle bundle have, which ones look at the same-ish and which ones look different. It's to describe this hom space how many connected components does it have? That's something we don't know. There could be a number, there could be infinitely many. Okay. How about how many come from bundles with Euler number 0? Or in other words, if I just give you a surface across the circle, okay, how many ways are there of picking out a foliation transverse to the fibers? You can do this sort of product one. You could do something else. Do they all look the same? Can they all be deformed one to the other? Okay. So the question is, can every horizontal foliation on the product, can every foliation transverse to the circle direction be continuously moved, deformed, to the product foliation? Okay. That's an open question that I think no one has the right approach to right now. But theorem that maybe gives us some hope. Okay. For the unit tangent bundle example, okay, and the foliation that I gave you, the endpoint one, instead of product on the product bundle, okay, the answer is yes. Okay. That's a theorem of Matsumoto from sometime in the 1990s. And stuff that I've done more recently is finding other examples, sort of understanding other examples where the answer is yes or sort of, examples of bundles that are rigid under deformation. And you know, the tools in this are part, as you might guess, part kind of hyperbolic geometry, okay, and part understanding these representation spaces for groups acting on the circle. So although we have a couple other examples, which has been kind of an ongoing mild obsession of mine, this kind of giant vague question and this specific instance of it are completely untouched. So I think this is a really fertile and rich research area that I wanted to advertise, draw some pictures, sort of show you a little bit about how you can very geometrically think about Euler numbers and circle bundles. And I hope that will pique your curiosity and lead to some good conversations. Thanks. Yes.
Does it get any better or worse if we replace homeomorphism with different one?
Probably the answer is different, but we cannot measure the difference. So for this theorem, the same thing remains true if you replace with diffeomorphisms. And for every sort of theorem we have, it remains true. But I suspect that the answer in general is different. So there are kind of lower dimensional examples if you look at foliations on, or if you, on specific manifolds with sort of not this transverse to the fibers thing, there's examples where it's different. So we suspect yes, but we don't know. Yeah.
Do you have a conjectured answer to that open question over there?
This one? Wait, this one?
Yeah.
Yeah. So I have a conjecture that I have a very bold conjecture which might be wrong. Okay. So the bold conjecture is that you can always deform one of these representations to have image in some kind of Lie group, subgroup of homeo of the circle. So like PSL2R, or one of these finite covers of PSL2R, or something like this. If that's true, then the answer to this is just 1. Okay. So I'll say that's the bold conjecture at the moment, but, you know, it's a conjecture by optimism, not by evidence.
What if we have a similarity on the surface, say a nodal point?
Yeah.
So is it a generalized notion of this foliation?
Totally, right. So, and that sort of corresponds to representations with kind of prescribed behavior for some element. So like, if you have a surface, you know, with a cusp or something like this, okay, you can take the element of the fundamental group that represents this cusp, and you could say, you know, or if this is a cone point or something, you would take about homomorphisms where this element is parabolic, or where this has finite order of order 3, and that's your cone singularity.
So this corresponds to holes for singular.
Yeah, for the right definition of what you want to think about singular structures. Yeah.
Is this like playing parallel transport?
Yeah, so another way to think about this is as a flat connection. Okay, it's telling you which way to move horizontally. Because I'm working with homeomorphisms, everything's topological. There's maybe no actual connection in the sense of differential geometry, so this is why you can think of the foliation, but if things are smooth, it's exactly equivalent. Yeah. Yes?
So what is the topology on this form from
Yeah, so okay, one or two representations close. So in homeo of the circle, I say two things are close if they take points to nearby points, right? Just the compact, you know, the usual like whatever you want, pointwise convergence or uniform convergence topology. And two representations are close if they take the generators to nearby homeomorphisms. Okay, so in 2 words, it's the compact open topology, but that's more precisely what it is.
So if I take two different homomorphisms,
Yeah.
so do they give rise to different, non-isomorphic foliation bundles?
Up to conjugacy, if they're not conjugate, they give 2 different things. Okay, and there's another notion you might want to generalize conjugacy by to prevent you from like taking, say you have a closed surface leaf, a section, you could change this to be like a whole bunch of parallel copies of it. You might want to say that's also the same. So you might want to say you can collapse intervals to points instead of just doing a conjugacy. But both of these are good equivalence notions.